Good evening, everyone. We are in the week 11 problem solving session of the course, Digital Controlling Switch Mode Power Converters and FPGA-based Prototyping. Week 11 is about design and validation case studies using digital voltage mode control and mixed signal current mode control. Let me share my screen. I hope my screen is visible. So, can you please confirm if my screen is visible? Yes, visible. Okay. So we can start. So this is week 11. So we are in the week 11 problem solving session, and it is mainly two parts. One is the design and the other one is the validation case studies. Using again two control techniques. One is the digital voltage mode control and mixed signal current mode control. And before we go into the week 11 outline, let me just summarize what we had discussed in week 10. So in week 10, we had discussed about the steps for FPGA prototyping of digital voltage mode control and current mode control. So again, in the last week, we had discussed mainly about the variable frequency. So week 8 is about digital voltage mode control and current mode control, but fixed frequency. So week 8 was about fixed frequency, and week 10 is about variable frequency. So last week we had discussed about variable frequency, and so we'll just summarize what we had discussed in the last week. So to summarize, we had started with the hardware demonstration of digital voltage mode control and mixed signal current mode control. So let me use a different color. Yeah, so in the last week, first we have started with the hardware demonstration. So we have displayed few pictures of the hardware while it is running in digital voltage mode control and mixed signal current mode control. And we have seen the hardware results and how the communication is happening between laptop to the FPGA to signal conditioning board to the power stage, and how we are displaying the data from the power stage, and how we are displaying in the oscilloscope. And how to use the oscilloscope we had discussed in last week during the microcontroller, and we had seen the dead time and other case studies. Also, how to get the frequency information and duty ratio information that we had seen in that week. And in the last week, in the mixed signal current mode control, we have discussed about the stability. So when it is peak current mode control, what happens when the duty ratio is 0.5? We have seen there are subharmonic oscillations. So how to compensate it? We got a expression for RAM, and there was a mistake. Banerjee has corrected me. So it was MC greater than M2 minus M1 by 2. So Banerjee, this is the equation, right? Can you recall? Hello.
Hello.
Hello. Yes, Banerjee, this was the equation, right? M2 minus M1 by 2.
Yes, sir.
Okay. So previously in the slides, it was written. Hello.
Sir, I have a doubt. In the week 10 assignment, could you please explain the last question?
Week 10.
Yes, sir.
Okay.
Assignment 10, last question.
Last question.
Yes,
Okay.
sir.
Okay.
It is based on constant off time.
Constant off time.
Yes, sir.
Okay. And are the answers shared with you?
Yes, sir. But there isn't any solution. For this, you have to refer to this lecture, they said, sir.
Okay. Can you recall what the question was?
Yes, sir. It is like a block diagram, sir.
Okay. And they're asking which is the constant of time modulator.
Yes, sir. From the lectures, it is clear that the constant on time negation itself gives the constant
Constant
of
of
time.
time.
Yes, but there is another option, sir, along with this.
Okay.
I didn't get it how it was solved.
Okay. Got it. Actually, currently I don't have the material for assignment done. So you do one thing. Tomorrow, the sir will be taking one live session. So you just drop that question in the forms that I think you have received the link, right, where you can drop the questions and they will be answered by sir.
Okay.
Yeah, you
Okay, sir.
just drop there. So tomorrow the session is from 5 to 6. So sir will be explaining that. Currently, I don't have the assignment with me, so I cannot open it.
Okay, sir, let me clarify one thing. Like,
Mhm.
for SR flip-flop you are taking,
Mhm.
like, is it always a set dominant, is it always reset dominant, or
Yes, it
constant
is
of time
always
it is the other
like
way?
in current mode control, like peak current mode control, we write the code in always reset dominated. Yeah, thanks for pointing out. This is one good thing. So set reset Q. So this is that switching pulse FSW, and reset pulse is coming from the comparator output. So plus will be IL, and minus will be I reference. So we always make it reset dominated. So whenever there is a reset, so at that time it will be, it should reset. So
Sir,
in
why,
our
sir,
case,
if it is the set dominant, what is the problem?
like there is no such problem as such, but in case when there is set as well as reset, we always try to reset because set is happening periodically, right? So it will anyway set, but reset is happening on the event trigger. So when that event happens, it should reset. So that's why we always give reset dominated, because when it gets reset, it will be again set in the next switching frequency interval. So
Sir,
this is
but there
happening
is a
periodically.
concept behind,
Sorry.
sir, there is a concept behind this, sir. Like, in one case, there will be some duty ratio.
Okay.
I am not clear whether it is exactly what it is.
Mhm.
But there is a point like that if it is set dominant, then the duty ratio will have some feature, whereas reset dominant, it has some feature. Like, the off time can be from 0 to 1 or something like that, sir.
Okay, where did you get this one? Is it from the SARS lectures or somewhere else?
Uh, so in the SARS lectures, he mentioned some references, right?
Okay.
Which was written by SAR itself.
Okay.
During the start of this course, I'd gone through that and I forgot to ask you. But in the recent days, when I am watching the previous lectures,
Mhm.
like control and tuning methods,
Mhm.
there he mentioned this too, sir.
Okay.
But I am not clear what exactly it is.
Okay. Is it like in the current mode control or where exactly you mentioned? In the
Yes,
voltage mode
sir.
control.
Like, I'm not clear where exactly it is, but in
So,
case of SR flip flop, there is that thing.
okay. Okay. I'm not exactly able to recall that which lecture it is from because it is in the previous course. Yeah. So, but what happens is maybe I can tell you one. Let me think of one scenario where it should be reset dominated. Okay. So let us consider one case study as such. This is the inductor current, and there is a step down. So inductor current will fall, and this is the inductor current, right? So if you consider switching pulses in between this region, there are multiple switching pulses, right? Do you agree, Banerjee?
Yes, sir. There will
Yes.
be switching
Yes,
pulse.
multiple switching frequency, and this is the waveform of IL, and I'll use a different color for I reference. So I reference, what happens is until this point it is in steady state, and after this point I reference has gone to some point, say something like this. I reference. This is the I reference. Okay. So now if you consider this region, from this region to this region, So it should not turn on, right? Because the current has to fall and it cannot turn on. So when reset becomes 0, reset, let me write. So reset is equals to two things. Reset is 1, reset is 0. Reset is 1 when IL is greater than I reference, and reset is 0 when IL is less than I reference. So until and unless, say, IL is greater than I reference, which means our inductor current is higher than the reference and it has to be brought down below I reference, right? So in this scenario where it is a step down transient, our I reference has gone down because the current has gone down and our controller says I reference is less. During this region, it should completely turn off, right? Because it has to go down. And that's why it is reset dominated. Had it been set dominated, what will happen? At every set, say inductor current is like this and it got reset. And if it is a set and it will go in the other direction and the reference is at the bottom. Okay. So in this case, what happens? The event will not happen and it is continuously set. You're getting what I'm trying to say here?
Yes, but constant on time and off time we are not talking, right?
So I'll come to that point again. So the
Okay.
first issue is, what if there is no event? In this case, because event will reset, right? So what if there is no event, meaning event is not there, so reset is 0. Or you can say IL is greater than I reference. In this scenario, IL has to be brought down. And if it is a set dominated, and if the set becomes 1, then IL will keep on increasing, right? And IL will is always greater than I reference. Say S is equals to 1, R is equals to 1, which means there has been a switching pulse, FSW pulse has come. Also, IL is greater than I reference. But I know that when IL is greater than I reference, irrespective of the switching pulse, I know that it should be turned off so that IL will fall down and it will go below I reference, which means when both set and reset are 1, based on the logic, so that the system will not collapse, I know that it should be reset, which means it is again reset dominated. This part is clear?
These are clear.
Okay. Now, coming to the other case where we are talking about the constant on time or off time. Say, let us talk about constant on time, which is a peak or valley. Is it peak or
Valley?
valley? Yes, valley. So constant on time, off time, on time, off time. Yeah, Shankar also mentioned valley. Yeah, it is valley current mode control. So it is again valley. So here again the issue is after on time, I will turn it off. So after on time, I will turn it off for that much or that amount of time until it hits the I reference. So this is the I reference and this is the IL. So now I'll consider one case where the inductor current is like this, and say after off time, say like I'm considering one scenario where so after off time, so it is like this. And what happens, say the reference has changed and it is beyond, say some case where I reference is above this IL. Then in that case, what happens? Assume that I'm assuming a case where I reference is greater than IL. Now what will my controller do? So until IL hits I reference, it will not turn on. So IL, so the converter is doing what? Converter is in off, say buck converter. Converter is in off state, right? So off state, my V0 will discharge, V0 will decrease. So if V0 decreases, V error is equals to V reference minus V0 increases. So if my V error increases, then my I reference increases. right? So in this case, I reference will be continuously increasing, but IL until it hits the I reference, it will not turn on. So what happens? It will collapse. I reference will completely become zero because it is not turned on. So in that case, what we had done, we had put something called minimum off time. We have put something called minimum off time and minimum on time. So after say some minimum off time, so it realizes that it should be turned on and not off. So after that minimum off time, my controller will check whether it has to be forcefully turned on or it can still continue doing off. So after minimum off time, the logic that we had discussed previously, it will check whether it has to be forcefully turned on or it can be turned off. So if it has to be turned on, then it will again turn on for constant on time. And after again minimum off time, it will check. So what will happen? Let me use a dark color. So after minimum off time, it will turn on. Say I reference is above, again constant off time, and until it crosses. So now it has crossed. So now it will be happening like this. So there could be one border case where it might not it might collapse, system might collapse. So for that border case, in the case of constant on time, we have minimum off time. And similarly, in the case of constant off time, we have minimum on time. So that at in such scenario where I reference is greater than IL, and the loop will keep on continuing because I reference will be keep on increasing and this will keep on decreasing. So it will not hit, it will always lie below I reference. So it will collapse. So similar scenario, it will be just the opposite for minimum of constant off time and minimum on. The same thing could happen in the fixed frequency also, where we have considered this. If it had been set dominated, then it will set and the inductor current will keep on increasing, right? The I reference is in this way and this will keep on increasing, and that we should not want. And there it has been reset dominated, which will consider this border case study. And here it is like constant on time different modulation technique. So this is the solution. One is the minimum off time and the other one is the minimum on time. So this part clear?
Yes, sir, clear.
Okay. So RAM compensation, and kindly take a note. This is correct. So this is correct, and I have modified in the drive also in the my notes. So this is wrong and this is right. I have made a mistake while typing that equation. So please note that, and if you had taken any notes, also change in your notes. And then we had discussed about voltage-based constant on-time control. So this is again voltage-based constant on time, not current based. So there is only one loop, voltage loop. And we had discussed about top-down design methodology and FPGA implementation. What are the blocks, quad modulator, what are the internal submodules of quad modulator, and the Verilog implementation, and also the hardware results. And in the other case, we had considered the mixed signal constant on as well as constant off time control. And we had also seen the top-down design methodology and what are the experimental results. And we have considered a comparative case study where we have considered few case studies, like what happens if I naught decreases for constant I reference. What happens if I naught increases? We have seen that switching frequency is dependent on I naught, either directly or indirectly. No, I mean proportionally or inversely. So we had seen that it has severe effect on switching frequency I naught. And if we don't want that to happen, then we have proposed some control technique exists, which is the peak current based adapt on time, where the ripple information is kept constant, whereas the off time and on time will vary depending upon the input. And here also we have seen that in the case of V input change, then it will have severe effect on switching frequency, also the ripple. And if we want to avoid that, then we had discussed about the adapt to on time. where the peak information is fixed. So on time will be adjusted accordingly so that the ripple will be constant, and the closed loop will take care of about the off time. So here we have discussed top-down design methodology and also the hardware results that SAR has shown for different V8, and we had seen how it will affect the on time. So on time is here related with V8, so on time will be adjusted accordingly. And then we have solved a few problems, two problems we had solved. So now coming to the week 11. So week 11 is
Sir,
just,
could you please explain? Sir, I have a doubt.
yes.
Sir, is ramp compensation is same as that of emulated ramp or something
No,
different?
no,
Both are
no.
entirely different.
No, actually ramp compensation and emulated ramp are two different things. So ramp compensation. And the second one is emulated ramp. So ramp compensation means if we consider one case where if we consider its application, it is the fixed frequency peak current mode control for duty ratio greater than 0.5. We have seen that it is unstable, and for it to make stable, we have to add additional ramp. So if it is unstable, we have seen that additional ramp has to be added. So ramp has to be added to IL to make it stable. So usually how it is, usually the case is we have minus plus is IL, minus is I reference, and the comparator is giving. So in the case of ramp compensation, what will be done is minus plus, this is I reference. So there will be a summer block. This is IL, and this is a some ramp, whatever, maybe I'm writing I ramp. So again, this is a fixed frequency, right? So the ramp will be something like this. Because it is fixed frequency. So now who will decide the slope of this ramp? Say M ramp. That slope information, like how much slope is needed to stabilize the system. How much, say MC, how much is needed? That we got the expression. Yes.
It must be greater than M2 minus
M2
M1
minus
by 2.
M1 by 2. So this is the ramp compensation, which you added to the already existing inductor current in order to stabilize the system. In these cases where it is the normal inductor current is not sufficient to stabilize. Now coming to the emulated ramp. So we had not actually gone into deep of the emulated ramp, but we had discussed something called fully digital in week 2 as well as week 3 MATLAB simulation, week 2 the architecture and sampling. So in fully digital, there are again two things. We know voltage loop is digitized or is in digital, and current is also in digital. So current is digital, which means we are taking a sample. So current sample is taken, and we are emulating the ramp in the digital platform. So you can consider it as a counter. So we'll emulate it at some slope, say fixed frequency, and then make it 0. And you can, it will not be exactly like this. So if you refer to the diagram, so emulated current will be something like this. So this is the on time, this is the off time, and so let me just clarify on this. So this is the on time, T on, and this is the off time because it is switching fixed frequency after hitting the I reference. Let me use a dark color. So after hitting the I reference, it will turn off, and from which point it will start, that is the sample that we have taken. So based on the inductor current sample, that decides at from what point I have to start the counter. And the slope of this emulated RAM MC, that also we had discussed in the week 2. So it is dependent on M1 as well as M2. So this we are completely emulating in the digital platform, and there is no such inductor current, or neither we are adding it to the inductor current. So we are completely emulating the inductor current based on the information of the inductor current. So we'll take a sample of the inductor current, and using that sample with the slope that we had derived or that we had obtained from the analysis, we'll emulate the ramp, and then this is the I reference of N. So this entire thing is in digital. So we are emulating completely in digital, whereas here that IRAMP that we are adding it to the analog current. So IRAMP is also analog. This we are writing the code in digital and passing it through DAC, and then that is happening. Is this clear?
Yes, sir, clear. But is there any case in which the RAM compensation is negative? Like,
No.
is there
Like,
any chances of taking MC with negative slope?
no. We need MC because the system is unstable, and in order to make it
Okay.
stabilized, we are adding it. If you add MC negative, it is destabilizing the system. So in that case,
Okay.
the system is already stable, and you are adding some instability, and you are trying to destabilize it. So say the system is stable and your MC is very, very less. And if you subtract it from I reference, say if you subtract it from I reference, it might have some effect, but it still might be stable. But if you keep on increasing MC, there will be a point where it is unstable. So we are adding it only to stabilize it. So we'll never subtract.
Okay. Sir, one thing, please clarify. Like, I am not clear whether it is correct or not, but I saw something like MC is subtracted from the I reference, I guess.
Yes. Yeah. So what, so this is the theory behind it. Now what we are doing is IRAMP is coming from the digital platform, which is going through DAC. So what else is going through DAC? I reference. So instead of adding IRAMP to IL, I can subtract the IRAMP from I reference also. So if I modify that, I will get something like this. So plus,
Sir,
minus.
this one is not clear, sir.
Okay, I'll explain. So first, let me draw and then I'll explain DAC. And we have a summer block here, plus minus I reference IL. This is IRAM. So what we are doing is our comparator is comparing IL plus IRAM with I reference, which will be equivalent to comparing IL with I reference minus IRAM. So assume all are constant. Say IRAM is also say some constant value. I am considering one case IL, IRAM, I reference. Say this is 1 ampere. Say consider no ripple for our ease of understanding. Say this is 1 ampere, say, and this is 0.5 ampere, and this is 1.5 ampere. So at the equality condition, I know that I reference is equal to IL plus IRAM, which is this aspect, right? IL plus IRAM is equals to I reference. Now what can I do? I can also write it as I reference minus IRAM is equals to IL, which is this scenario. Is this clear? Is this part clear?
Sir,
So
in the above case, IL is subtracted from
no,
I reference is subtracted from
no, it is not subtraction. It is comparator. It is comparator. We are comparing. So we are comparing IRAM added to IL with I reference. Say that is the condition. Say whenever it hits I reference, I am considering IL plus IRAM should be equal to I reference, because that is the case. So I have considered IL plus IRAM is equals to I reference. And if you go by this way, I'll get this 1 ampere, this 1.5 ampere, and this 1.5 ampere. which is equal to the I reference 1.5 ampere. The same can be done here, where this is 1.5 ampere, this is 0.5 ampere, and this will be 1 ampere, 1 ampere, and this is also 1 ampere. So it is just the same thing. Numerically, I am modifying it here so that it will be easy for me, but it is not mandatory that you should only go by this way or you should go by this way. Both are same. According to one's ease, they can either do the method 1 or method 2. So
Okay, sir. Thank you, sir. It's clear now.
okay. So now let us go into the week 11. Week 11 is about design and validation case studies using digital voltage mode control and mixed signal current mode control. So I would say that this week 11 is just a summation of week 5 plus week 8. So in week 5, if I remember, we had discussed about the design of voltage mode control and digital voltage mode control, and the design of mixed signal current mode control. How to get KPKA, KD in the case of PID controller, how to get KPKA in the case of PI controller, what is large signal tuning, what is alternate method in voltage mode control. Those aspects we have discussed here. And in week 8, we have discussed the FPGA implementation of digital voltage mode control and mixed signal current mode control. So combining these two in this week, we'll again just quickly refer to the design case studies that we have studied, and also implementing that in the FPGA prototype, and see how these two like two different designs that we had studied vary from each other and what is its effect. Using the experimental, we'll validate our theory, and also using the MATLAB simulation, we'll validate our simulation, whether simulation is closely matching to the hardware or not. So these are the aspects that we'll discuss. So the first part is the digital voltage mode control. First, I'll quickly recap the digital voltage mode control architecture, and then we'll go into the simulation as well as hardware results comparison. And then we'll quickly discuss about the design, which we have discussed in week 5. So we'll not go into the details of the design aspects, but I have put some slides so that we can quickly recall what we had discussed in the earlier session. And then there are two designs which we'll use this here, and we'll do a quick comparative study of those two designs. So if you recall, one is the pole zero cancellation method and the other one is the alternate method. We'll just quickly summarize in the upcoming slides also. The second part is the mixed signal current mode control. Again, we'll do a quick recap of mixed signal current mode control. And if you remember, in mixed signal current mode control also, there are two different design case studies that we had considered in the week 5. One is with load current feed forward and one is without load current feed forward. So again, we'll just quickly summarize these design aspects, which are again discussed in week 5. And then we'll do a comparative study of these two and what difference that load current feed forward make on the performance of the hardware and other aspects like overshoot, undershoot, settling time, all these things. And the other one is the multi-mode digital control, which is a very crucial topic. So in the upcoming weeks, I will be teaching multi-mode control implementation and everything. But in this week, it is just an introduction. So we'll spend some time learning the PWM. What is PWM by PSM? Why do we need it, and how to implement? What is the logic behind it, and all those things. And then we'll quickly solve a few problems. So coming to our first topic, so digital voltage mode control, again, we had discussed this in week 2, the architecture and sampling methods, and week 3, the MATLAB simulation, and week 5, the design aspects, and then week 8, the FPGA implementation of fixed frequency. And in week 10, last week, we had discussed the voltage-based constant on time. So we had discussed this in many weeks, and in week 11, we'll see the experimental versus simulation. So if you want to compare the simulation, how good our simulations are compared to the experimental. So we'll see what is the importance of the simulation and how much we can rely on the simulation. And we'll again quickly recall the designs that we had discussed in the week 5, and further designs, we'll quickly do a comparative study and see what are the differences. So just to summarize, let me change the color. So we know that this is the digital voltage mode control in Buck converter. So the V0 is being passed through a resistor divider, which will give V feedback, passed through analog to digital converter, and then subtracted from the V reference to get the error voltage, and then passed through the PID controller to get the controlled voltage, and then it is being compared with the external RAM, which will have, it is like a counter based DPWM. And it is again giving the reset pulse and the set pulse, which is going to the dead time block that we had discussed, which will give PWM high as well as PWM low. So if we see a Verilog module of the cell, it will look like this. So the feedback is coming to the ADC, which is on the signal conditioning board, giving the ADC data, which is going into the FPGA. And FPGA has a main clock, F clock, and this is for the transient load or reference transient. And this is the module, main module. It again has sub modules inside it. It is giving the frequency for the sampling of ADC, and the outputs are PWM high, PWM low, and this Q load is the switch that is responsible for the load transient. So as SR has explained, there are two resistors. One is the R1 and one is the R2. So R1 is high resistance, this is low resistance. So if you want to give load step up transient, you have to close this switch using Q load. And if you want to give step down transient, so initially it is closed, you will give Q load 0, so it will be open and less current will flow, which act like a step down load transient. So now coming into the same FPGA implementation. So this is just the same block diagram drawn in a different way. So this is again V0 with the gain V feedback going into ADC, giving the digital number. So the block is digital inside the red block, subtracted from the reference to generate error voltage, going into the PID controller, which generates the control voltage, compared with that modular counter-based DPWM, which is again using F clock, and the switching frequency is FSW. After comparing, it will generate the reset pulse. The set pulse is coming from the switching frequency clock, generating the Q pulse. Now it goes to the dead time, and we had discussed the dead time logic also, its implementation, giving PWM high and PWM low. Now we had discussed in the MATLAB implementation. So when we had done the MATLAB, we have normally done the normal voltage mode control. But if we want to exactly implement what that hardware has, then we can also implement this KF gain. So this KF gain can also be implemented, so that V0 is stepped down to this V feedback, same as this V feedback. And say this is for reference transient. So this digital voltage mode control block is something similar to this block. So just to create the same scenario, SR has used the same set of names, and it is generating the Q. In the hardware, we had not given any dead time. So in the hardware, no dead time was given, but you can use the same logic that was discussed to generate the dead time. And this is the sampled voltage. So it is QF into V0 of n. So the sampled voltage is this voltage. This is the V SAM or VS. Again, there is less than a minute. So if this meeting ends, quickly join so we can continue our discussion. So this is the oral MATLAB implementation model. If you go into this model, what does it contain? So it contains exactly the same thing that we had discussed in the week 3. So this part is the sampling. You can consider it as ADC. So we had discussed it is event trigger, and it depends upon the event. Now this event is a uniform switching frequency.
Sir, while using this MATLAB simulation, like without digital controller, customized block, if I use ready-made block, is there any problem, sir?
Ready-made block in the sense which block? For which block are
That
you?
is already available discrete transfer function block.
For the PID controller.
Yes, sir.
Okay.
Will I get output the sampling time at which I want to take the sample? That is different story.
Yes.
But I'm getting some oscillations, sir. Whether what's the wrong thing I'm not getting there.
Okay. Okay, so if we talk about custom based PID controller, there are a few things that we can discuss. One is like we are getting this PID, custom based PID using the difference equation. And it is not fixed frequency. It can be variable also. So when we consider variable frequency operation, our control voltage should change with respect to the frequency, which is varying. If you use a custom PID block that the MATLAB is providing, it is fixed frequency. So what happens is it will change the control voltage in a fixed frequency format, and the converter is operating in a variable frequency. So there will not be any synchronism with that. So either the control, say if the switching frequency of the converter is more than the frequency at which this is changing, so the converter will operate at higher switching frequency, but the control voltage will change after few cycles. And in the other case, when the switching frequency is lower than the frequency at which the controller is operating, so within a single switching cycle, the control voltage will be changed multiple times, which we do not want. We want it to be changed once in a cycle. So it has to be customized. So that's why here we are creating the trigger event. So whenever this trigger comes, then only the controller will start performing, and it will generate this VCon. So if this is event based, instead of the switching fixed frequency switching pulse, I'll generally give the event and it will be triggered with the event. So that is the advantage of the PID, custom based PID. But in your case, I'm not sure why the oscillation is coming, whether it is due to this. In the case of fixed frequency, you can use that custom block and there will not be any issue. But in the case of variable frequency, this will create issue if you use in the variable frequency and you cannot use them. But whether this
I'm
is the reason
using
in your
digital voltage mode
oscillations,
control itself, sir.
I'm not sure, because we have to check if there is any mistake, or you have to check. Maybe you can run in the open loop, and if it is working fine, then you can know that there is issue with this thing only in the block, and then you have to debug block by block and check, because again debugging means we do not know in what part of the block the error is. So we have to go step by step. First run in the open loop and see if it is working fine, then power stage is fine, then controller has error, so you have to again go debug block by block, check the input voltage, output voltage of that block, whether it is working fine. Block by block you come and you have to debug it.
Okay, sir.
So again, that is the advantage. And here this FSW is uniform sampling because it is fixed frequency. We can do the uniform sampling once in a cycle, and that sampling delay again we can customize in this block. It depends upon what sampling delay that we would like to keep. We can incorporate that. Now this sampled voltage is subtracted from the V reference, giving rise to the V error of N, which goes into the digital PID controller, giving us the control voltage. And the ramp here we have considered the smooth analog ramp. This is analog ramp, like it is not a counter, not counter based DPWM, not this is not counter based DPWM. So for the ease it was considered, but you are free to use counter also, not counter based DPWM, because this is a ready-made block, so we had used it. Again, counter based, you have to use other block and see how you have to work with that block, and then comparing it gives the reset pulse. So this FSW is in one data type, and this set needs in another data type. I think S should be Boolean. This will be double. So for that purpose, we will use data conversion. So it is nothing but the same information with a different data type that this block will understand. So for that data convert block is used, and then it generates to gate pulse, and we have not included the dead time, but dead time can be included, and yeah, so that can also be included. But for the ease to start with the basic thing, we have directly used the gate pulse and Q bar, because it is simulation. That time is actually not needed because it is an ideal case, but in the hardware, that time is always needed, and you cannot give just the complementary, else one of the switch will blow up. So this is the MATLAB implementation. So now coming to the case studies that Sar had discussed. So Sar has discussed multiple case studies, but we'll be discussing only few of them. So in the first case, we are discussing about the load transient. So step up load transient. So one is the MATLAB results on the left side, and the other one is the hardware results. So these are the results. If you see, this is V naught and this is IL. Similarly, this is V naught, this is IL, and this is the IL, and this is V naught. Okay, I think I have made a mistake. The right side is the MATLAB, left side is the hardware results. So this is a mistake. I'll change in the while uploading in the drive, but sorry for the mistake. So left side is the hardware results, right side is the MATLAB results. So if you see, IL is quite closely matching, and this is sufficient. So the simulation is just to give some idea whether we are able to tune it properly. So now it is giving us almost close behavior with the IL. So in this case, we know that, okay, it is giving some decent result, and it is V naught is also quite closely matching. So my aim is bet, and the simulation whatever we had made, it should be sufficient. So I'll get close idea about the hardware, and this is fine. So this is so we'll consider 4 such case studies. One is the load step up, and the other one is the load step down, reference step up, and reference step down. So this is the first one, and the second one is the load step down. So it is just the same, and it is also okay. It is quite closely matching with the inductor current and with the hardware results also. And my V naught is also quite closely matching. And this is just sufficient to first implement my idea in MATLAB and check whether the response is according to the requirement, settling time, all those things. And the same I can implement in the hardware. So the simulation is mainly just to get an idea how the system is working, what controller that we had used, whether it is able to give the objective, like the required settling time, or shoot, undershoot, all the requirements. So first we'll just simulate it and check, and then we'll implement in the hardware. But how good is our simulation? That again depends upon what all device parasitics, all the physics that we had included. And based on whatever model that we had done, it is quite closely matching, and it should be sufficient to first test our idea in the simulation before going into the hardware. Again, it is all safety, right? So whatever control techniques that we had implemented, if the system is going unstable in the simulation, then we can rectify it before going into the hardware. And if you directly go to the hardware and if something goes wrong, any device might get damaged, and again you have to replace the device, which we want to avoid. So first we'll always check in the simulation, make sure that everything is working perfectly fine, our logic is good, then only we move into the hardware. And also we can get some idea whether our logic is working according to what we had thought in the beginning or not, whether it is reaching within the settling time, whether the undershoot and overshoot is within our range or not. Now the third case is, again, I'll change this MATLAB results, hardware results, so it should be the other way around. And this is the third case study, reference transient from 1 volt to 1.1 volt. And this is the inductor current, and it is also quite closely matching, and this again is sufficient. Similarly, our V naught is also quite closely matching, and yeah, our model is good for a decent estimation of the hardware results. And the fourth case study is the reference step down. And
Sir?
yeah,
Sir, you are creating periodically the change in reference, right? In the
yes,
hardware setup.
yes, yes.
Why not in case of MATLAB you can do the same?
Yeah, this is just the same. In the MATLAB also we had done the same thing, but we had zoomed in the this part. So let me go back here. So the V reference actually we Sar had used a step function here. If you see, yeah, Sar had given a step function here. Let me use a different color. So Sar had given a step function here, which is only a single step from V reference to V reference plus delta V reference. But you are free to give a square function for the V reference. So this will be V reference plus delta V ref, again V reference. So this can be done. So we have that flexibility. Sir had only wanted to give step function, so he had given step function, but you can use a square pulse and you're free to give. Same for the load transient, we can give multiple load transient. In the hardware also, if you want only one step, we can give that step. And if you want square, we can give square. Again, it is up to the user choice how he wants to give. So the last case study is the reference step down transient, and they are perfectly, not perfectly, but some to some, not some extent, to majority of the extent, it is closely matching. If you see here, this kind of behavior, it is quite able to capture that behavior, and all the undershoot and settling time, they're mostly matching. So it gives us almost a 90% idea about the hardware. So we can always refer to the simulation that we had discussed, and it is good enough to get an estimation of the hardware implementation. Now, there is this another case study that Sar has shown for a different set of KPK AKD. So if you see here, the red green color is the hardware in all the 4 pictures, and the red color is the simulations, MATLAB results. So in the until this point, we had compared the MATLAB image and the hardware result image. Only we have compared the image, but we have not overlapped one on top of the other, because when we save the data from the oscilloscope, we can choose in what format we want it to be saved. Say image PNG, BMP, and .csv file. So what this .csv file means, it will save the data, the quantized data. So it will be saving multiple data taken at that clock. So if say it depends upon the oscilloscope how many samples it will take per second. So accordingly, it will take that sample, and this can be opened using Excel sheet. So when you save that .csv file in that pen drive, you will find there will be an Excel sheet, and the data has 2 columns. One is the time series, and the other one is the data series. Now we have to access this time and data series and plot in the MATLAB, on top of which we have to run our simulation. So we can overlap them and see to how much extent it is matching. And we can see there is mismatch. Of course, there is mismatch, and but to some extent it is matching, but still there is mismatch, which could be of, again, many reasons. One is we have not considered the counter-based DPWM. We have considered normal DPWM. I mean, not even DPWM, we have considered the analog smooth RAM, and we had not incorporated dead time. And there could be some non-model dynamics that we have not included. Non-model dynamics that we had not included in our simulation. So some kind of mismatch is always expected, because it is quite impossible to go to like 99% matching with the hardware, and with MATLAB it is again difficult. We should go to the higher simulation software. So with what MATLAB can offer, these are the matching that we are getting, and by incorporating this, we can get somewhat better results and somewhat better matching. But this is what has been observed, and there is some mismatch. So in the simulation, it is somewhat over damped, whereas in the hardware it is somewhat more damped. Again, it could be because of some aspects that we had not included in the simulation. And similarly with the step down result also, the same thing has happened. The hardware result is somewhat settling faster compared to the simulation. So there we have there is some mismatch, which could be of, again, whatever reasons that we had mentioned. It could be any one of them, and we can try to improve. But the simulation is anyway just to give some idea of how our algorithm or our control technique is working before we go into the hardware. So we'll get just some estimation, and there will be some mismatch between those two. So until this point, is it clear?
Sir, I have a question.
Yeah.
Sir, like zero order hold is in general used as an ADC or a DAC, sir, in general.
ADC. Zero order hold means we'll take the data point, we'll hold. We'll take the new data point, we'll hold. We'll take the new data point, we'll hold, which is just an ADC, right?
Sir, for reconstructing which we choose
Sorry.
for ADC, for analog to digital, we are using this thing. For reconstruction from digital to analog, how we can convert?
Like we are using DAC, right?
Okay. Physically, how it will be, sir?
So I can use some other space. So maybe this space, or let me bring it here. So what happens is when we say analog to digital converter, say if we talk about the ADC that we had used, say here if it is 1 volt, and we had discussed it is a 2's complement of Q1.9 format. So it will be digital equivalent number of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So I think it will be 1023. So when we convert this analog voltage to digital voltage, it will be just a number, and that number means nothing until we give it some value. Like we are giving a Q format, right? And that gives us some value about the like voltage. What is the value of the voltage? So now we had given it a format Q1.9. So it will be 0.1, 2, 3, 4, 5, 6, 7, 8, 9. So it will be 2 to the power minus 1 plus 2 to the power minus 2 plus up to 7 2 to the power minus 9, which will be almost 0.99 volt, close to 1 volt. So when we say analog to digital, it is just converting that voltage to its digital equivalent number. And again, when we say DAC, it is converting a digital equivalent number to analog voltage. Say again, it is Q1.11 format with offset binary. Say I want the output voltage to be 1. In 2's complement, sign MSB will be 0 for positive voltages, and in offset binary it will be 1. So 1.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it has here this is 1 bit and this is 11 bits. So when we are saying digital to analog, it takes in a 12-bit digital number, some number which has no meaning until we give it some value. So we have defined the Q format. So now this will give me some information, like it will be 2 to the power 0, which is the first bit, plus 2 to the power minus 1 plus 2 to the power minus 2 plus up to 7 2 to the power minus 11, which is almost close to 1 volt. So we are giving the digital value from our FPGA, which is going through that DAC IC, and it takes those all 12-bit and whatever manipulation or whatever mathematical thing that it is doing inside, it will directly give one analog voltage, which is according to the DAC. The DAC we had chosen Q1.11. So for the DAC that we had chosen, it will give us analog equivalent of 1 volt. So when we say digital implementation in FPGA, so everything is in bits and numbers. So it is, we are operating in binary, so it is zeros and 1. So our output, say 1 volt, if we want to take it to the FPGA, it is not just 1, right? 1 means 0 or 1. So 1 means only 1. But if we want 1 volt, it should be some equivalent digitized number. So that who will do that? ADC will do. So ADC will quantize it and give us the 10-bit number. Depending upon its span, the output might vary. And for the ADC that we had selected, which is 10-bit, it is Q1.9 format. And now we can get the information about what is the bit size, what are the digital equivalent number. And now this digital number, we are manipulating it, PI controller, PID controller, all clock generator, all the sub modules and modules that we had discussed in the earlier weeks. And then finally, we are generating one 12-bit equivalent number, which will be fed to DAC in the case of current mode control. And this DAC is not needed in voltage mode control, which will generate this equivalent reference analog voltage compared with the inductor current. Is this part clear?
Yes,
Hello.
sir, clear.
Okay. Okay.
Yes, sir, clear, clear.
Okay. So now we had discussed about some MATLAB model aspects, as well as how much it will be matching with
Sir?
the hardware. Yes.
Sir, in the last, while comparing simulation and hardware results,
Mhm.
so the CSV format we are taking
Yes.
from the hardware from the DSO,
Yes.
and sir, this time series data we are taking.
Mhm.
Sir, how do we ensure that the time series data on the DSO and the MATLAB has a equal number of data?
No, it might not have equal number of data. If you see here, the voltage is somewhat quantized, and see the data size might not be equal, but the data at which the time at which the load transient is happening should be equal. Say if I consider a single clock cycle of inductor current, I do not care about how much data is available per switching cycle FSW. It will be pretty much high, and that's why I can see it is purely smooth function. I will only care about my switching frequency, so that I can overlap the hardware inductor current on top of my simulation inductor current. Okay, and also I care at what time instant my hardware is seeing a load step transient, and at what time instant my simulation is seeing a load step transient. That should be synchronized. But the number of data inside within a single switching cycle, I'll not bother, because it takes mega samples per second, and the data will be huge, and it will give me smooth. Only I have to match that this event. Let me use a different color. So I have to match the time scale so that this event and this event will overlap on top of each other. So the data can be many mega samples, but in the case of MATLAB simulation, it will be smooth. But in the case of the data, it is digitized. So it will be, say, from this point to this point, it takes 10 to the power 6 samples, or depending upon the oscilloscope, how much data. It will be smooth. And I only have to bother that this point and this point of the hardware and MATLAB is overlapping. That Sir has discussed in his lecture how to map that, so that we can see the complete overlap. If you see this event and this event and this event, they are mapped. So we are seeing one hardware, and on top of that simulation. So we are seeing both overlap, and this load transient instant, this had to be overlapped. So this we had to do manually. So we will plot MATLAB separately and hardware separately, and we have to either time shift it, and also we have to adjust the offset also. So accordingly, the adjustment has been made, and then we are viewing this results. I hope this part is clear. Hello. Okay, sir, understood. Yeah, thank you. Now we'll go into the design aspect, which were discussed in week 5. So all the details are discussed in the week 5. So I'll not go into the details, but I'll just quickly summarize. So this is the model. We had discussed about the continuous time model with delay. So we had seen that this model is quite close to our discrete time model, and we had concluded that this model should be sufficient enough to design a controller, and that's why we are using this. This is the delay, and the rest of the part is continuous time. And if we get the K loop, we'll get this expression. Now what we had done is, we had designed the controller in the first method, pose zero cancellation, where we are cancelling this with this, and we are cancelling the tau d s plus 1 with 1 plus s by omega s. So k1 is 1 by q omega naught, k2 is 1 by omega naught square, and tau d is RCC. And after cancelling it, this is the final K loop expression that we got. And we know that GC is a PID controller. So we will get the information of K1, K2 in terms of KP, KI, KD. And when we back calculated, we had discussed these derivations in the week 5, so we'll not go into the detailed derivations. So then we got this KP, KI, KD values. Again, these are analog. So if you want to convert into digital, it will be KI into T and KD by T. So that we had discussed, and this is the phase margin, and this is coming because of the delay term. So this is the basic introduction to designing the PID controller with the continuous time with delay model. And these are the PID controllers. So you can always refer to this week if you have any doubts, or you can go to SAS lecture as well. And then we have designed controller, and we also.
Sir, could you please explain once K loop, how you got K loop of S, please?
Okay. So K loop, FM, FM. V in by alpha, V in by alpha. And this is completely cancelled. This also completely cancelled. The numerator completely cancelled. Denominator has only ester. So ester. And here Ki, here Ki. And here e to the power minus STOD, and here e to the power minus STOD. So that's how we are getting K1.
No, sir, the first equation which you have written,
Yes,
FM
so K
into
loop
V in by
is
alpha.
K loop is GC into e to the power minus STOD into FM into GVD, this loop. So GVD is this. So this is GVD of S.
GVD of S is nothing like,
This
what is
thing.
GVD of S?
GVD of S
It is a duty to voltage
due to
ratio.
output voltage. So it is V naught per tub of S by D per tub of S. So these derivations are discussed in the earlier course. And if you need, then you can go through that course and derive it. But if you do not have time, you can just assume that this is the GVD of S. But whenever you get time, I recommend you to go through that previous course. But yeah, you can just remember that this is GVD of S, and you can design the control.
Sir, loop means we have not to consider V reference, right? Just the loop only.
Like when we say loop, what we do is we break the loop and we calculate the gain from this point to the entire point without actually the sign. So if say if the sign is not considered, so from this point, say if we go GC into e to the power minus STOD into FM into GVD. And this is
Sir,
the,
then
like,
what is the starting and ending point, sir?
Like you can just break the loop here, and you can start from this point, and you can go from this point to this point.
Yes, sir. Like if that is the thing, V is the starting point and V out is the ending point.
Something like that you can say.
Sir, but actually V naught comes when there is a VG, right? GVG.
V naught comes when there is GVG. This one.
Yes, sir. Yes.
Like we are talking about this loop. GVG comes when you consider about that input to output, which is audio susceptibility closed loop transfer function. But we are talking about the K loop. So, yeah.
Sir, why we are not? The audio susceptibility comes with the feed forward term, right?
Yes, V input tab, yes.
Okay, then it is actually not included in the controller. That's why we are neglecting it, right?
Not neglecting it because it is not the part of the loop.
We are not considering it.
It is not the part of the loop.
Okay.
But now when you consider V out per tub by V in per tub, then this loop will come. So this is the open loop transfer function. This is the open loop transfer function. So now this is a closed loop system. So now if you consider V naught per tub by V in per tub, it will be GVG by 1 plus K loop of S. So this comes from the controller systems that we had learned in the UG. Or if you face any difficulty, you can derive it also. There is no issue.
Okay. Sir, like there are actually two loops, right? We are only for one loop.
No, there is no other loop. Like these are directly only this is the closed loop. There is no other closed loop, right? Only one closed loop. I can see only one closed loop. The others are directly added to this summer. There is no closed loop.
Okay.
So in the week 5, we have also discussed about the different steps. So we had discussed how we'll choose. First, we'll choose 1/10 of the switching frequency, and then from that 1/10 of the switching frequency, we'll compute the phase margin, because omega c we know, and then we'll get tau d. So then tau d is RCC, so we'll compute our phase margin, whether that phase margin is greater than 60 degrees or less than 60 degrees. If it is greater than 60 degrees, we can continue. If it is less than 60 degrees, we have to reduce the omega c such that our phase margin is greater than 60 degrees. When finally it is say greater than 60 degrees, then first we'll compute Ki, and then we can compute Kp, and then we can compute Kd. And we have discussed in the digital domain, Kpd is same as Kpd. Kid will be Ki into T, which is the switching clock time period, and Kdd is Kd by THW. So these are the aspects that we had discussed multiple times, and they are also in the week 5. You can go through my YouTube video, or you can go through source lecture as well. So this is the first method that we had discussed. And in the second method, where we had discussed about the alternative approach, in the alternative approach, we have discussed that Kd should be chosen 0.1 like a fraction of C, because this voltage derivative is similar to current mode control with load feed forward. So it will act like a feed forward, which will improve the response. And we had discussed Y fraction, because if Kd is much higher, it will inject noise. So it should be like a fraction value. And you can also choose 0.2C, 0.1C, but just to start with, Sir has selected 0.1C, and tau d Sir has considered tau T by 2. And this Ki is coming from the small signal pole zero cancellation. So it is just same as the pole zero cancellation. So if we consider here, we have omega c alpha Vm by V in. Omega c alpha Vm by V in. And omega c Sir has considered 1/20th of FSW. So 2 pi FSW by 20 into alpha Vm by V in. So this expression will give us this expression. So now we got Kd, tau d, and Ki. Now how will I get Kp? So you should again manually tune Kp. So you will put Kp some value and see what are the gain crossover frequency and what is the phase margin. If it is not like meeting our requirement, then you again change Kp and then make sure that this will happen. So this is another method that we had discussed again in the week 5. Also, you can go through this lecture 45 if you have any doubts, or you can go through our week 5 YouTube session also. Now we will quickly discuss about the design comparative study. So sorry, this is not voltage based part. I'll modify these mistakes and I'll update the final version. So this is digital voltage mode control, and pole zero cancellation. Using pole zero cancellation, we got Kp Kd, and using the alternate approach, Sir has calculated the Kp Kd. And using this Kp Kd, there will be a comparative study and how alternative approach performs better than the pole zero cancellation. So in the case of load step up and load step down that we had considered, red color is the pole zero cancellation. So red color is our method 1, which is pole zero cancellation, and the blue color is our method 2, which is alternative approach. If you see in the case of inductor current, there is not much noticeable difference from the MATLAB simulation. But if you consider the voltage response, the alternative approach is much well damped compared to the pole zero. Also, the settling time is less. Ts or small ts is less compared to the pole zero. So we can see and say that in the inductor current, there is no much difference. Both are almost same in the case of overshoot, in terms of overshoot as well as settling time. Whereas in the case of V0, we had seen that alternative approach provides better damping. Also, the settling, it will try to reach the settling time much faster, a bit faster than the pole zero cancellation. And the same has been implemented in the hardware results, and Sir has shown the hardware results. And I'm not going into the details. I just wanted to mention and focus on the part where alternative approach performs better than full zero isolation. So with this, we complete the voltage mode control. Now we'll quickly go into the mixed signal current mode control aspects. Again, this mixed signal, we first started the architecture and sampling methods in week 2. Then we went to the week 3 MATLAB case studies. And week 5, we had discussed the design aspects. And week 8, we had seen the FPGA implementation. And week 10, we had seen the variable frequency caught constant on time as well as constant off time. As well as adaptive on time. So similar to what we had done in digital voltage mode control, first we'll see the experimental case studies, also the simulation case studies, and then we'll discuss the 2 design methods that we had discussed already in week 5, and then we'll have a comparative study of the 2 methods that we had discussed in the week 5, which are mainly without load feed forward, and with load feed forward, and what difference does it make by adding that load feed forward information. We'll go into those aspects. So first I'll summarize. Let's have a very quick recap. So the voltage is stepped down, and then we get V feedback, which is going into the analog digital converter, gives us the digital equivalent number subtracted from the reference, giving us error. Now it passes to the PI controller, gives the control voltage. Then we had discussed the design, the importance of the current reference in terms of keeping saturation and converting 2's complement to offset binary, and the Q format matching. All these manipulations will be done in current reference, and also protection purpose, like peak current saturation as well as valley current saturation we can incorporate in the code we had discussed. And then now it goes to the digital time lock, which will give equivalent reference voltage, because we are dealing with the voltages, compared with the V sense is the equivalent current sense. We have again discussed in week 6 how the current is being sensed, different type of architectures, like using sense register or using DCR sensing, and we are doing the non-isolation current sensing. There are isolation current sensing also, like LEM sensor, Hall sensor, different kinds of sensors, current transformer, all these things we had discussed. And now this gives us the reset pulse, and set pulse is coming again from the digital controller, and this is giving Q, giving rise to dead time, PWM high, PWM low, going to the switches. There is less than a minute, so if this meeting ends, quickly join so that we can continue our discussion. And then if we see the FPGA implementation, so the left hand side will be similar to the voltage mode control. We have ADC, V feedback, FADC, Q tran to decide load transient or reference transient, main clock 100 megahertz clock, and the Q comp is the comparator output. Now it goes into the main block, which is the mixed signal current mode control. Output DAC data is going into the DAC compared with that current comparator, and this Q comp is again going back here. Also we have PWM high, PWM low, Q load going further. So the same thing will be there, and this is for the load transient, and we had discussed this in week 8 also, and week 10 as well. And this is the FPGA implementation. So the same thing written in a different format. So V0 with the gain giving rise to V feedback, and analog to digital converter, ADC data going into that register, or it is just the same thing, giving N out and subtracted from the N reference, giving rise to N error. And then we have PI controller, and then control voltage, current reference for the saturation, also converting 2's complement into offset binary. And then we have digital time lock converter, and then we have the comparator here, which will again go to the reset SR flip-flop or SR latch, and then dead time generation, giving us the high side gate pulse as well as low side gate pulse. Now, let us quickly see some hardware results. Yes.
Sir, that Qtran is used to select for select between DCM and CCM, right?
No. This Qtran is can be either 1 or 0, and one is reference transient, and one is for low transient. And if it is selected for low transient, then this Q load will send the pulse to that output register that we have. So this is R1 and this is R2. So this
Okay.
Q load. Okay. So let us quickly go into a few hardware results. So these are the gains KPKA that are selected. We'll consider load transient as well as reference transient. So this is the IL and this is the V0, and here this is the V0 and this is the IL. So as you can see, this is somewhat sluggish response, and the settling time is high because it is overdamped as well as first order. And we'll see how to tackle this undershoot and this V0 aspect in the case of load feed forward. So this is just one case study that SAR has considered for load transient and reference transient. So load transient, reference transient 1 volt to 1.1 volt, and accordingly for 1 volt with this resistance value to this resistance value. So one is 1 by 13.5 amperes and one is 1.1 by 0.33 amperes, and here the voltage is from 1 volt to 1.1 volt. So this is just the introduction, and now if we go into the design aspects that we had again discussed in the week 5. So we had discussed this in week 5. We are using the continuous time with delay model, and similar to what we had done in the voltage mode control, we are doing the same thing, K loop of S, and for the pole zero cancellation, we are cancelling this with this. So now we'll get omega CZ information. So that omega CZ we can convert back into KP as well as KI. And if you cancel this and this, and in the case of designing, SAR has neglected this. So this is ESR information. To keep it simple calculation, SAR has neglected this. So we'll have this R information, and in the controller we have KI by S. So in the controller we have KI by S, the KI by S, and here e to the power minus S to D, e to the power minus S to D. Now if we consider the bandwidth omega C, from that this closed loop bandwidth we'll get KI, and if you substitute that KI here, we'll get the KP information, and these derivations we had done in week 5, and the phase margin is this 90 degrees minus omega C tau D, which is quite similar to the voltage mode control. If you discuss about the design aspects and the steps how to tune, it will be similar. So we had discussed in the case of current mode control, we can go up to omega C by 8, and this SAR has discussed in the previous course. Again, this comes from the small signal model validity. In the case of current mode control, the model small signal is valid till 1/8 of the switching frequency. So we can go to the bandwidth of 1/8 of the switching frequency. So you select this, and then again you compute the phase margin, whether the phase margin is less than 60 degrees or not. If it is less than, we have to reduce the omega C and then check whether the phase margin is greater than 60 or less than 60. Suppose our phase margin is greater than 60, then we'll, using this formula, we can compute KP as well as KI, and then we know that KPD is KP and KID is KI into T. So from this, you will get KP KI. In the similar way, SAR got the KP KI values here using this same technique. So this is the first technique where we had not given any load current feed forward and just a pole zero cancellation. Now, if we go into the second one, which is the load current feed forward. In the week 5, again, we had discussed. Also in the lecture 49, Sir has discussed the large signal trajectory. So this is the large signal tuning. It is okay if you do not completely understand the calculations. You can go through the lectures, but if you are feeling that it is a bit tricky, just learn how we had decided. So we had large signal trajectory based controller tuning. So we had considered the trajectory and we are shaping the trajectory and using which we had designed the KPK. So we have considered that line. And here we had the I naught with some gain Kn. So that information is coming here. And I'll not show the calculations here because we had discussed the concept in week 5. And from there, Kp value was obtained and Ki value was also obtained and Kn value was also obtained. But there was one issue that these gains are very high. These gains are very high and they are not practically implementable. So then what is the solution? So what they had done is they had considered Kp to be 20. And if Kp is 20, what is the gain with which Kp should be multiplied? That is obtained by this K attenuation. So now this is my Kp obtained or optimal. Into this K attenuation gives me the value of 20. So after getting that K attenuation factor, I will multiply Ki as well as Kn with the same factor. So Kn is equals to 1 into K attenuation. So it will be K attenuation and Ki will be K attenuation into this whatever value that we had obtained. So it has two things. The first half is this is the first half where the gains are designed based on the large signal trajectory shaping, and the second converting them into the gains which can be practically implemented using open power in the digital controller. So now there are two methods that we had discussed, and this is the load current feed forward. So the details and the calculations I have discussed in the week 5 also. If you face any difficulty, please go through that week 5. So these are the two methods, and from these two methods, we can get Kp, Ki, Kn. Sorry. So now we will go into the comparative case study of load current feed forward and without load current feed forward. So using the design techniques and the Kp, Ki, Kd values that we had discussed how to derive, Sir has done Kp, Ki. In the case of this case, we have Kp, Ki. In the case of this, we have Kp, Ki as well as Kn for that load current feed forward gain. So this is for the load current feed forward gain. So if you see the inductor current, there is no that much quite improvement or difference as such. But if you see the voltage waveform, here there is undershoot and large settling time. Here also large settling time and overshoot. Whereas here, as if there is no overshoot or undershoot, because we are adding that load current information in our control technique. So it is taking care of it, and ideally there should not be any overshoot or undershoot, but our load current feed forward information cannot be that much accurate. So there will be slight or no. If you see, there is very negligible undershoot or overshoot, which will completely reduce our V not undershoot and overshoot, and there is like recover. There is no overshoot to recover. So here it takes so much time for the recovery time. So to recover that same voltage, it needed a lot of time. Whereas here there is no overshoot and undershoot, as if it is always regulated at that V reference voltage. Even for high step currents, Sir has shown the results that it is observed that V reference is having no overshoot or very less undershoot overshoot. So till this point, is it clear? Hello. Yes, sir. Okay, now we'll go into the other case study, which is the reference transient. So in the reference transient also, sir has, I think this is also, actually this is not reference transient, sorry, again my mistake. This is with the high step up load transient. I'll modify this, sorry for the mistakes. I'll modify this and I'll update the final one in my Google Drive. Here you can see it has undershoot, overshoot, whereas in this case, negligible undershoot. Here there is no overshoot, and here there is very negligible. Also, we can say there is no undershoot, overshoot. So this is the advantage of the load current feed forward. So we have no undershoot or no overshoot, which will substantially reduce the capacitor requirement, or the recovery time will be very quick. So that is the advantage of the load current feed forward, and sir has shown multiple hardware results, and I have taken only few of those. So this completes our mixed signal current mode control discussion also. If you have any questions, you may ask. Do you have any questions? Yes.
Sir, when there is in our conventional stage, whenever there is an increase in load transient, there will be a decrease in output voltage, right?
Yes.
Sir, in this, how that feed forwards is taking care of that and making that to be much.
Okay, so in the case of without load feed forward, whenever there is a inductor current information, our I reference will change based on the V naught itself, right? So this is without load current feed forward. But in the case of load current feed forward, our I reference will have this Kn into I naught information as well as V naught information. So it will not wait for the V naught. Whenever there is a load current response, it will directly update the I reference. So accordingly, our controller will take action. And this is one way of saying that. The other way is the output impedance. So our output impedance will give, say, V naught put up by I naught put up is equals to Z out. Say my V naught put up is equals to Z naught into I naught put up. So whenever there is a perturbation in the output current, how much perturbation will be there in my V naught? That defines the voltage undershoot or overshoot, and it is dependent upon Z naught, because I naught is given by the load, and the only thing that is in our control is the Z naught. So here Z naught is the closed loop output impedance. Closed loop output impedance. Say for example, I will get a Z naught that is equal to 0. Then my mathematical analysis says my V naught put up is 0, which means even if there is a load or even if there is no load, my perturbation in the V naught is close to 0 or like exactly 0 or close to 0. So it will be very minimal. So this completely relies on the assumption that our closed loop output impedance is nearly equals to 0. And in the lecture, not sure, in between 107 to 109, sir has discussed the closed loop output impedance aspect, that how this load feed forward is able to achieve that output impedance close to 0, as if the output voltage is not affected because of the load current step up or step down. So sir has shown the calculations, I have not shown, but it is dependent on the output impedance. So output impedance in the case of load feed forward is very minimal or close to 0, because of which our V naught perturbation is very minimal or close to 0. That's why it is either very minimal or 0. So there is, as if there is no change in the output even if there is a load current step up or step down. You can go through sir's lecture where sir has shown the mathematical analysis, but I have not shown it. Is that clear, Rashekar?
Yes.
Okay.
Yes, sir.
Okay. So till now we had considered about two case studies, design and case studies. One is the digital voltage mode control, and the other one is the mixed signal current mode control. We had quick recap of the architecture, FPGA implementation, and then we had discussed about the design aspects, and then we had seen MATLAB versus hardware overlapping, how close were the matching, and then we had seen some hardware case studies for two different methods of the design case studies that we had discussed for digital voltage mode control in week 5. Similarly, we had seen the two different design case studies for mixed signal current mode control that were discussed in week 5, which are load current feed forward and without load current feed forward. Here, pole zero cancellation and alternative method. So what are the advantages that we are getting using the method 2 compared to method 1? And here we have seen the hardware results, and SAR has also shown the we have seen the simulation results compared to study, and SAR has shown the hardware results. And in the other case, we had seen the hardware results of load current feed forward and what its impact. We have seen that V not overshoot, undershoot is minimal or close to 0 because of that load feed forward action. Now, this completes our voltage mode control and mixed signal current mode control. Now we discuss something about multi-mode, which is actually very important topic, and again it is used in many of the products for the reason that we'll discuss in the upcoming slides. So first we'll discuss about the need. So what is the need and design requirements, and also introduction to PSM and PWM. So we will be using two different modes. So that's why it is multi-mode. So one mode is PSM, the other mode is PWM. Again, this 110th lecture number 110 is just an introduction. Sir discussed this in lecture 110, but in detail we'll discuss in week 12. So in week 12 we will discuss in detail, and Sir will be showing two things. One is PSM PWM, and the other one is PSM PFM. So this we'll discuss in the next week, but today we'll only discuss about the need and the design requirements and some introduction of PSM and PWM. Yeah. So just to quickly summarize, and this is the digital voltage mode control that we had discussed today also in many weeks also. So this is the digital voltage mode control. And coming to the digital PSM, we had discussed that there will be fixed duty ratio, fixed frequency pulse. Either this will be given or the pulse will be skipped. So the one is the charge pulse, the other one is the skip pulse. So depending upon the requirement and depending upon this comparison, it will say whether it is 0 or 1, saying 0 or 1. So this will be QPWM or 0. So either it will charge or it will discharge, or which is called a skip pulse. So the implementation Verilog coding had already been discussed in week 8. So you can refer to the week 8 lectures if you had any questions. But this is the introduction for the digital PSM and the digital voltage mode control. Now coming into the need. So why do I need multi-mode digital control? So what is meant by multi-mode and why it is needed? What are the advantages? What are the challenges? So if you consider say buck converter, and these are the loss versus I0. So when we cross certain value of I0, say I boundary, I say, switching losses are always constant because it is fixed frequency of operation. After some time, this conduction losses will cross the switching losses, and also below at light load, switching losses are dominant. So at light load, switching losses are dominant. So if I want to reduce the losses at light load, the only thing I could do is I have to incorporate those control techniques which will reduce my switching frequency at light load. And we had discussed how PSM operation will do, and we had seen when SAR has reduced the I0, we had seen that skip pulses will increase and the charge pulses will eventually decrease. So here both are PWM, and if we use PSM and PWM, we have seen in the case of PSM, FSW will decrease when I0 decreases. So when I0 decreases, the charge pulses will reduce and the skip pulses will increase. effectively the switching frequency reduces, switching losses will reduce. So this is the advantage of the PSM at light load condition, because in the light load, it will operate in the DSM and it will reduce the switching losses. Now we'll see how
Could you
this.
please explain this one?
Yes. So in the case of light load conditions, if you operate with fixed frequency, say light load, our switching losses are constant, and we don't want that. We want our switching losses to reduce. So when we operate in PSM, we have realized in the week 8 that when I0 reduces, our skip pulses will increase, which means our switching frequency, effective switching frequency will decrease, which means our switching losses will decrease. So when I operate in PSM at light load, my switching losses will decrease as I0 decreases, which is I want, which is the thing that I want. And here it is constant, here it is reducing. Although it is not zero losses, but the losses are getting reduced, because zero losses is next to impossible. There will be anyway losses, but efficiency I would like to improve. In the case of PWM at say I0 or no load condition, there will still be switching losses and it is constant. The output power is close to zero, but the losses are there, which means the efficiency is very poor, almost very less value. So that's why if we operate in PWM, the efficiency in the light load condition will be very poor. Now we are replacing that PWM with PSM. What it does is it reduces the switching loss. So if my I0 is say 0.1 ampere, my switching losses will be very less because the switching frequency will be very, very reduced. So there will be losses, but not as much as it is in the case of PWM. So it will almost maintain high frequency, which is much superior than PWM. And in the case of many products also, where efficiency matters, they use multi-mode. So they operate, they'll have one light load modulation technique, and after certain current requirement, they operate in the other technique. So which is beyond some current load current, they'll operate in the other modulation technique, say peak current mode control, fixed frequency, or it could be variable frequency also, depending upon what control technique they're using. So this is the need for multi-mode digital control. Why we need multi-mode? Because to improve the efficiency, which is the main thing in many of the products. So just to summarize, the number of skip cycles increase as the load current decreases. So when the load current decreases, number of skip cycles increase, which means the switching frequency decreases. Also, when the switching frequency decreases, switching losses also decreases with the load current, which again improves the light load efficiency. So this is the advantage of PSM or operating under PSM at light load condition. And when we move into the high load condition, again it goes into CCM. So there is no point of discussing about PSM in the CCM operation. So we'll move on to the PWM. So again, PWM fixed frequency or variable frequency. So there can be two scenarios. One is PSM or fixed frequency PWM. The other one is PSM or variable frequency PFM, which sir will be discussing in the upcoming week. But this is just an introduction. So we are talking about the need and the challenges. Is this clear? Until this point. Hello. Sir, what is the significance of static curves in P-loss? So static loss is just again some other loss that is considered, and it is like here it is almost constant, and here for the PSM loss it is very less, and which again it is an improvement in the case of efficiency. So here switching losses are also reduced, and the static losses are also reduced. Now if we go into the multi-mode digital control, so one question that arises is how to write the Verilog code. And when will we like transition between PSM to PWM? The transitions should be smooth, and how it is happening, all these aspects, these are the challenges. And there is something called integrator wind up. So there should be something called anti wind up, which we'll again discuss in the upcoming week. So these are some of the challenges that are there. In the when it comes to the multi-mode digital control. So the first aspect is there should be something, some bit which decides whether it is PWM operation or PSM operation. And the entire thing is similar to the voltage mode control. The input is V feedback, FADC, Qtran, F clock, here PWM high, PWM low, and this is for the load step transient. So what this block contains is, it contains two submodules. Now this decide whether it will operate in voltage mode control or PSM. So how this bit is decided, that again will come into the next week, but we just wanted to discuss about this block. So what this block contains. So we know about the digital PWM and voltage mode control, and we know about the digital PSM. So it contains both the blocks. So V naught with the gain KF coming to V feedback, then analog to digital, then ADC data. Both needs ADC data. Now first we'll come to the voltage mode control. Subtracted from the I reference, generating error. Then it goes into the PID controller, generating control voltage. Then it is compared with the counter-based DPWM, generating the reset pulse. Then set pulse is coming from switching frequency, and the dead time, it generates high side as well as low side. This part will come later. So this is the digital voltage mode control. Now we'll go into the other part, which is the PSM. So ADC data is coming, and again we are subtracting it from the N reference minus N out. Now the error is again going into the PSM logic, whether PSM logic is 1 or 0. If PSM logic is 1, then this fixed frequency gate pulse will be given into the output, which is the charge pulse. And if QPSM is 0, which means it is the skip pulse. So QPSM is again 1 or 0. 1 is for charge pulse, and 0 is for the skip pulse. So this Verilog code that we had discussed in the earlier sessions, also earlier weeks. So we are not going into that. So now PWM will give two high side gate pulses, and PSM will give two low side gate pulses. Now which high side gate pulse will I take? Because if it is PWM, then I should take the PWM gate pulses, high side as well as low side. If it is PSM, then I should take the low side of the PSM. So there is something called MUX, and MUX has selecting line. So if PWM / PSM, this is again 1 bit. If it is 0, it is meant by PWM operation. If it is 1, it is meant by PSM operation. So if it is 0, our PWM high will be the high side gate pulse coming from the PWM. Similarly, if it is 0, it is the low side coming from the PWM operation. Now, what if it is 1? If it is 1, let me use a different color. So if it is 1, then what will happen is, it will take the high side from the PSM, and similarly here it will take the here it will take the high side, and here it will take the low side, and low side is 0 because it is always off. So we are not giving any pulse to it, so it is 0. And this pulse, PWM or PSM, this pulse, this bit will decide whether we are getting the data from the PWM or whether we are getting the data from the PSM. So is this point clear until this point? So it basically consists of two blocks. One is the voltage mode control. The other block is the PSM block. And in the voltage mode control, entire logic is same. And in the PSM also, entire logic is same. And The only confusion comes at the output, because it also has high side pulse, it also has high side pulse, it also has low side pulse, it also has low side pulse. So we use two muxes. One is mux 1 for high side and the other one is mux 2 for the low side. So depending upon the logic that we have created, whether it is 0 or 1, the corresponding high side or low side pulse will be given to PWM high, PWM low, and this will go into the power stage gate pulses. So yeah, as you do not have any questions, we'll go into the problem solving session. So we have 3 problems today. Coming to the first problem. So just to summarize, we had discussed about the digital voltage mode control, mixed signal current mode control, and then PWM PSL. Now we are solving the problems. So the first problem is about the digital voltage mode control of buck converter. So I am saying consider a buck converter operating under DVMC with the following parameters. Find KDD, tau D, and KID if the PID controller is designed using alternative method. So I have mentioned that it is designed using alternative method, and this is the voltage mode control of buck converter. I have given input, reference, L, C, FSW, VM, alpha, and R. So how do I solve this question? KD by TSW. Yes, so KDD is KD by TSW and KID is KI into TSW. But how will I get KDD KI? If we refer back to the alternative approach, we have derived that KD, tau D, and KI. So KD is nothing but 0.1 into C. C is how much? 400 microfarad. 400 microfarad. Now my KDD is KD by T. So T is how much? Switching frequency is 200 kilohertz. So my TSW is 5 microsecond, 5 into 10 to the power minus 6. So you just have to substitute that TSW and we'll get this TSW and substitute it back into this expression. We'll get the KDD. And tau D is nothing but T by 2. So tau D is 2.5 microsecond. And now coming back to KI. So KI is 2 pi, alpha is 0.99, VM is 10 volt, FSW is 200 kilo by 20 into V input is 12 volt. Now this gives me KI analog voltage and KID will be KI into T. So that's how I define or derive KID, tau D as well as KDD. But how will I do KP? For KP, again, we have to do the manual tuning so that the loop bandwidth as well as phase margin requirements are met. And that doing mathematically is difficult, so that's why I have not asked KPD. But whatever that can be done mathematically, that those type of questions you can expect in the exam. So is the first question clear? Hello. Yes, sir. Okay. So now we'll go into the second question. Again, this is there in the slide 17, so you can refer back to the slide 17, so you can get the control details. Now the similar question. So for mixed current mode control, I am asking KPD as well as KID using pole zero cancellation. So if we go back to the pole zero cancellation, we'll get the controller details, and I'm saying bandwidth of FSW by 10. So we had discussed FSW by 8, but I'm asking for FSW by 10. So all the necessary details are given, and we know that Ki is omega c by r. So if I calculate Ki, which is omega c 2 pi fc, which is FSW by 10 into r. So my Ki is 2 pi, FSW is 200 kilo by 10 into r is 0.1. So now after getting Ki, I'll do KID is equals to Ki into T. And what is my time period for 200 kilohertz? It is 5 microseconds. So my tau will be the same as previous question. T is 5 microsecond. After getting Ki, what will I do? I will do Kp is equals to Ki into RC. So what will I do? Kp is equals to, so the denominator becomes 1. So it will be 2 pi into 200 into 10 cube into R is 0.1 into C is 400 microfarad. So 10 to the power minus 6. So if I calculate 2 pi into 2 is 4 pi into 10 to the power 5 into 0.1 into 4 into 10 to the power minus 4. So 10 to the power 5 into 0.1 is 10 to the power 4, which gets cancelled with the 10 to the power minus 4. So my Kp is 16 pi. So this is the Kp value. And I know that Kpd is equals to Kp, which is 16 pi. That's how I'll get the Kp as well as Ki values for the pole zero cancellation of PA controller design of buck converter operating under mixed signal current control. So is this part clear? Hello. Okay. So it is clear. Now coming, so again, this is in slide number 26. If you have any doubts regarding this, you can refer to that slide. So the last question is the PSM PWM. So now tell me which one is what. When the load decreases, what happens? Skip cycles increase or decrease, or switching frequency increase or decrease? So load is decreasing. Again, there is less than a minute time. So if this meeting ends, you just quickly come back. So this is the last problem. Maybe it will be a few minutes. So if this meeting ends, kindly quickly join back. So when the load decreases, yes, Shankar is saying skip cycle increases and FSW decrease. So when the load decreases, number of skip cycle, if this meeting ends, quickly join back. And if the skip cycle increases, switching cycle will increase or decrease. Switching cycle will decrease. And what happens when the load increases? Hello. Skip cycle decreases and frequency. Yes. So just let me. So when the load increases, the skip cycles decrease. So the switching frequency increases. Yeah, Banerjee, you may. Again, this is in slide 32. If you have any questions, you can refer to this slide. Yeah. Banerjee, you may ask questions.
I'm fine. Sir, I'm finding difficulty in finding this controller design, sir.
Okay, like in the sense.
Like, sir, there are two models, like small signal model and large signal model, right? Yes, for which thing we are actually designing the controller, sir, and why there are like small signal modeling and large signal modeling? Could you please explain that?
Yes. So we have two design methods. One is the small signal. The other one is the large signal. So in the case of small signal, so first let us consider small signal model. So small signal model is considered based on the perturbation. So there will be this steady state term plus some perturbation. So what happens is if I consider IL, it will be IL steady state plus IL perturbation. And say this is IL of t. Similarly, VC of t, it will be VC steady state plus VC perturbation. So it lies on the fact that IL perturbation is much less than IL and VC perturbation is much less than VC. So we consider some small perturbation around that steady state and we get that small signal model. So again, I'll not go into the too much details of how we are getting that model, which is very well taught in the previous course. You can refer to, it is in lecture 20 to 30. So it is in between 20 to 30. So from this, they'll get this small signal AC model. So from this small signal AC model, Sir has derived this small signal transfer functions. So whatever transfer functions that we have used to derive the controller gains like GVD of S, GID of S, GVC of S, GVG of S, and ZO of S. So all these are small signal transfer functions, which means like it is only for small signal and very small perturbation, and they have limitations. So it is based on some assumptions. So these are based on some assumptions. So they have some model validity. So these models are not always valid. So they have this model validity and validity. So the model validity is they are valid till FSW by 10 in the case of voltage mode control, and current mode control we can go up to FSW by 8 as well. So this creates the limitation of our controller to operate at a bandwidth of 1/10 switching frequency in voltage mode control and 1/8 of current mode control. Say if I want to achieve faster response, I cannot use this model because this model the model itself is not valid. So the model will not give me the correct information about the converter beyond the switching frequency by 10 bandwidth. So when I want to design a controller so that my converter operates much faster than 1/10 of the switching frequency, I cannot use this model because the model itself is not valid. I cannot use that. So what I have to do? I have to rely on a model where this small signal thing, this approximation is not considered, which is the large signal. So in the large signal, there is no approximation. So if we go back to the week 5 where we have considered the trajectory based control, sir has considered the actual trajectory of IL and V0, how IL and V0 changes with low transient. So how from one steady state point to other steady state point, this IL and V0 will change. So considering that IL and V0 and assuming that I want my IL and V0 to move in a particular direction, I want it to be happening in one on state plus one off state. So this was the target while designing that. So in order to achieve this, sir has considered what is the IL and V0 trajectory, and then solving the mathematical equations, sir obtained Kp, Ki, and Kn. So here we have not considered any such assumptions, and we have not considered any small signal assumptions. Here there are no limits. So our model can be used to design to achieve bandwidth greater than switching frequency by 10. So our converter could be much faster with having a bandwidth greater than FSW by 10, which cannot be done using this model because the model itself is not valid. Say I want to use some model and the model itself is not valid, then I cannot use that model, right? So for switching frequency greater than for the bandwidth greater than switching frequency by 10, this model is not valid. So this model is not valid. Model is not valid. So for that, I cannot use this small signal model. So I have to use or rely on some other model, which is the large signal tuning, where we consider the entire ripple information, everything, and we do not consider any assumption. So, and we shape the trajectory. So sir has considered the trajectory based, and there are no limitations. We can design controller using both the methods, but here the bandwidth is limited. Bandwidth is limited to 1/10 of the switching frequency. But here there are no limitations, and we can design the controller beyond the bandwidth of 1/10 of the switching frequency, which sir has shown, and I think he has also shown the hardware simulation results. Yeah, that is all about small signal, large signal. So in order to achieve higher bandwidth, which is not possible in small signal because of the model validity, we are going for the large signal tuning. And the large signal tuning has been discussed in 49 of this course as well as the previous course where sir has discussed in detail. So I suggest you to go through the previous course also, that particular lecture if you are interested in that. So where sir has discussed in detail, and then you might get some better understanding.
Okay. Sir,
Yes.
like I have two more questions.
Okay.
Like, sir, if this is the case, then I can use large signal modeling and it can be
Itself.
used for anything, right?
Yes, yes. Now the question is why we are learning small signal, because large signal tuning is not quite simple and it is somewhat complex, as you can see, compared to the small signal. So when we actually start with a controller, we first want the converter to operate at to operate in the closed loop, and first we are not bothered about the response. First we wanted to operate under closed loop with some gains. But how will I know the gains? So first we'll do the small signal thing, so that it will give me some estimation of controller gains, and I can operate with this even though limited 1/10 of the switching frequency. But say I do not know anything about KP, KD. What values will I put? 111, 10, 1, 2, 3. I cannot randomly put now, because it has to be designed, and directly going to the large signal would be difficult. So just to have some basic understanding of what values I have to put. So in order to go into that ballpark of that KD values, we start with the small signal pole zero cancellation, which is again very rudimentary method to get, so that we can get that okay, KP should is approximately 10, KD is approximately 0.1, KD is approximately 7. So now I got those values. If I want to improve it, I can manually tune KP, KD around that ballpark. But in order to get into that region, I have to have some method, easy method to start with. So we'll start with the small signal, and you can manually tune around that values. Now my converter is working. Now my the other requirement is to improve the response. How I can improve? Whether that small signal is sufficient, yeah, then my work is done. But if I want to improve it so that the bandwidth is more than 1/10 of the switching frequency, then I'll go for large signal tuning. So yeah, that is the method.
Sir, then what is this concept of bandwidth greater than FSW by 10? And like, I'm not getting the physical significance.
Actually, when we go into the large signal, there is no such question as Bode plot, because there is no model. So you can consider in terms of the speed with which the converter reaches from one steady state to other steady state. So just think in this way, like the small signal model, you have considered KP, KD values you got, and you have given some load transient, and the time it takes to reach that new steady state in the case of small signal, and the time it takes to reach that new steady state in this large signal case. That is the difference. In the large signal case, it will be much faster and superior, maybe with less undershoot overshoot aspects as well. Whereas in the case of small signal, it will take some extra time. And that is what this speed of the controller is about, right? How fast it will react and take the system from one steady state to other steady state. So it is basically on how fast it is. I don't remember exactly, but Sir has considered this case like the comparative study of this MATLAB case study, and I have also shown. So if we can go to that one such scenario, but so here, as you can see, alternative approach reaches somewhat faster compared to the pole zero cancellation, and also the undershoot overshoot are reduced. Similarly, SAR has a paper of large signal PID tuning of buck converter, where SAR has shown different control methods comparison of large signal tuning, small signal PID, and small signal something called type 3 compensator. You can refer to that paper, and there you can actually see the difference, how much improvement that large signal tuning offers compared to small signal tuning.
So, but what is the, sir, you're saying that the concept of bandwidth is nothing but reaching the steady state, whether quicker or slower, right? Is that the thing you are saying, sir?
Yes, yes.
Okay. Actually, what I'm thinking is like the change the transient for which it is occurring, I thought in that way. Is that completely wrong, sir?
No, like, can you repeat? I could not follow.
Like what I'm thinking is this bandwidth all comes into the time for which the controller will react to a transient if at least the disturbance exists for that specific time.
Sorry, can you please repeat it?
If the like disturbance, if it exists at least for minimum time, then only the small signal model will react. Whereas the large signal model can react for that disturbance even for a short interval of time.
It is like, it again depends upon how much time we are considering. No, it is actually not that. Like, because if the, like, again we are saying how much time we are considering, because even in large signal tuning, even in small signal tuning, we are taking one sample per cycle in both the cases. Say before we take a sample, the disturbance is gone, then our ADC will not capture that disturbance, and neither the small signal nor the large signal will try to capture. But if that ADC captures that small signal as well as large signal, how fast does the converter react to that disturbance and come back to its initial condition? That defines the, like, bandwidth, you can say, or the speed, because the ADC has to capture the data, right? We are using the same hardware, everything, only the gains are different.
And one more thing is, like, sir, what is this concept of power spectrum, sir?
Power spectrum is that frequency components that are available in the that waveform. So
but
like,
why it is named power spectrum?
Like, it actually it is dependent to that power spectral density, and it depends upon the harmonics. So that's why, like, they call it power spectral density. And one thing is, when they define, or like they make a product, there will be some stringent requirements that the higher harmonic should not cross this much amount of magnitude. So it should be like distributed. So the spread spectrum should be distributed, and the magnitude should be somewhat smaller of like each harmonics. If you consider, SAR has shown that FFT, and when there are harmonics, we have seen that the peak are not just switching frequency and integers of switching frequency, but also fraction of switching harmonic switching frequency. That's why we are calling harmonics. So how to distribute these peaks, that SAR will discuss in the next week 12, and SAR will discuss something called spread spectrum. Something called spread spectrum. Sir? Yes. This will be taught by SAR in the next week, so we can discuss in the next session. Yes.
Sir, in the small signal model, basically we are saying when we are using the small signal model, we are considering the circuit is already, Buck converter is already in the steady state.
Yes, and we are considering perturbation.
Yes, sir. But how to take that circuit from
one steady state to the steady state? Yes, good question. So now what happens is, let me just go back to that small signal model. So if it is a disturbance, then it will damp out that disturbance and it will go to the previous stage. Say, where is my
sir, could you please repeat his question once?
So he is asking that small signal model that we are talking about, it is just perturbation considered around the steady state. But how is it going from one steady state to other steady state? Like, if V reference is 1 volt, we are considering the perturb model around that 1 volt, and we have got that small signal model. But he's asking whether if V reference changes from 1 volt to 0.1 volt, then how is our model able to take that converter operating at 1 volt output voltage to 1.1 output voltage? So let us consider this reference transient. So initially V reference perturb is 0 and V reference is 1 volt. Now V reference perturb is 1.1, V reference, not V reference perturb. So now my new V reference is 1.1 volt. 1.1 volt. So what is my V reference perturb? My V reference perturb is 0.1 volt. So there is a perturbation in the 0.1 volt, which is the reference perturbation, which means my V0 should perturb also 0.1 volt so that my error becomes 0. So my new reference has come. So again, this V0 should track that reference and it should go to that new steady state, and it should stay at that new value so that again my error becomes 0. So this is reference transient. And in the other case where we talk about load transient, say I0 is 1 ampere and the new I0 dash is 5 amperes. So my I0 perturb is how much? 4 amperes. So my I0 perturb becomes 4 amperes into Z0. It is again negative. So there will be this V0 perturb. What will happen? It will fall, right? We have discussed when there is a load step up, V0 will fall. But my in this case, when there is a load transient, my V reference perturb is 0. And say my V0 perturb is become negative, it becomes say some minus 0.1 volt. Now my V reference is 0 and V0 perturb is 0.1. So error is positive. Accordingly, the controller will change the V0 perturbation so that it comes back to this V reference perturbation, which is 0. And V reference perturb is 0, meaning it is coming to that original steady state, which is 1 volt. So perturbation is 0, but the steady state is 1 volt. So the perturbation is around that steady state. So here I0 perturb is 4 amperes, which is the new steady state. And accordingly, it has influenced the V0 perturbation. Now the controller is acting in a way so that this V0 perturbation will come back to its initial state, which is 1 volt. So V reference perturb is 0. Also V0 perturb is 0. Is that clear, Rashekar?
Yes.
Okay.
Sir, please repeat it once, sir. I
Yes.
didn't get.
Okay.
The question is clear, but your explanation.
Okay. So there are two cases. One is the reference transient. The other one is the load transient. In the case of reference transient, my V reference initially is 1 volt, and my V reference, the new value V reference dash is 1.1 volt. So my V reference perturbation is 0.1 volt. So there is a perturbation in the steady state value itself, and it is 0.1 volt. And initially my V0 perturb is at 0, steady state. Now my V reference perturb has become 0.1 volt. So it is 0, it is 0.1 volt, it is 0. Now what error is doing? Error is 0.1 volt, and my controller will give the it will give the new control voltage, and it will try to increase the V0 so that my V0 perturb soon will become 0.1 volt and my error becomes 0. So this is the new steady state, right? At new steady state, V error is 0. V reference is 0.1 perturb because I have given transient, and my V0 perturb is also 0.1. So my V0 perturb is 0.1, meaning my V0 is V0 steady state. What is the steady state? 1 volt plus V0 perturb. So it becomes 1 volt plus 0.1 volt. So it reached 1.1 volt. So my controller has taken action in such a way that V0 is going into the new steady state, which is 1.1. So this is about the load reference transient. Now coming to the load transient, my V reference perturb is 0 because reference is not changing, and V reference steady state is 1 volt. And V output steady state is also 1 volt. And now I am perturbing the I0, which means from 1 ampere load, light load to 5 amperes I am changing. So I0 perturbation is 4 amperes. So there is a new steady state for the I0, and the perturbation is 4 amperes. When the I0 perturbation is 4 amperes into Z0 with a negative sign, what it will do? It will reduce the V0 perturbation, right? So V0 perturbation has become negative, which we also know from the load response. Any load response, if we see V0 has become negative, right, initially. So that V0 perturbation will become negative. Now V naught put up is say 0.1 volt. It has gone to 0.1 volt. My V reference is not changing, right? V reference is 0 and V reference is 0.1 and my V error is again positive. So again, the loop will take care in such a way that it will reach a new steady state where my V naught put up will become 0 again. So my V naught put up will again become 0 volt because my V reference is 0. V naught put up 0 volt and steady state 1 volt is nothing but my V naught value is still at 1 volt. But what is the change? My I naught put up has become 4 amperes, which means I naught previously, which was at 1 ampere, has gone to 5 amperes, and my closed loop has taken care such that V naught, there is a change initially that it has become negative, but the controller has taken care so that it came back to that steady state. So here at this condition, V naught put up is negative, but the controller has taken action. So at this instant, V naught put up is again becomes 0. Perturbation is 0, but there is a steady state value, which is 1 volt. So my V naught is at 1 volt, but there is no perturbation because it has reached its previous value. So that's how my controller will take action on whatever disturbance. Say if it is disturbance, I reference perturb, I naught perturb will be 0. V reference perturb is also 0. So that disturbance will be nullified. So the controller will take action so that that disturbance will be damped out and it becomes 0 and it will not affect. But whereas if it is a new steady state, then the controller will take action accordingly so that it will reach that new steady state. So is this point clear?
Sir,
Yes.
sir, this small signal model will take only this load, so reference transient reference variation and then load current variation.
Yes.
Sir, if there is any other disturbance,
Yes.
apart from these two,
Yes.
how will the small signal model will react to that, sir?
Okay. So let us consider another case study where say there is some disturbance, noise. Say there will be a feedback gain here, right? Say some noise has added in order V naught put up, which is 0 volt, and some noise got added and the noise is not there, or say some noise got added, say n put up, noise put up is there, which will change this volt value, which will change this value, which will change this value, and because of the noise, say my V naught put up has become 0.01 volt. Now V reference put up is 0 volt and this is 0.01. Controller is negative, so accordingly it will change the control voltage so that this noise is nullified and I will get again 0 volt here. So the controller will take care. Whenever the controller sees there is an error voltage perturbation, it will start acting and it will nullify that effect so that it will reach that new steady state. And in the case of noise, the noise will be removed because it has added some additional voltage in the loop, which makes the error voltage negative. So it will change the V naught pattern and the noise will be like rejected. Noise, disturbance rejection and noise attenuation. So noise will be attenuated, and if there is any disturbance, that will also be rejected. Is this part clear?
By this this FSW by 10, this limit is saying about this small signal model will reach the new steady state only up to that FS by 10.
Like that
beyond
is the
that,
speed.
it won't reach a steady state.
Yes. Like it is not that it will not reach. The model will only be able to let us design a controller that has the bandwidth of 1/10 of the switching frequency, and that you can consider that decides the speed of the controller. So the speed at which the controller changes from one steady state to other steady state is equivalent to bandwidth. So using the small signal, the controller will put the maximum limit of the speed beyond which you cannot go because the model itself is not valid.
Okay, the beyond FS by 10, the response will become very sluggish.
Yes. And yeah, beyond FSW by 10, you cannot like design the controller also. So there will be a maximum limit or the maximum speed with which the controller can go from one steady state to other steady state. using the small signal model, and that is the limit beyond which you cannot do anything. So if I want it to be much faster, the model is not valid, so you cannot use that model, and you have to go through the go with the large signal tuning where there is no model validation, model limitation, and where we can make it much faster depending upon, there are different control techniques which are not discussed. One such control technique is the large signal trajectory based control technique that was discussed, but there are several other nonlinear control techniques which can also be used, and which are not discussed because it is beyond this course syllabus. I hope your queries are clear. And one thing I would like to announce. So tomorrow there will be one doubt clearing session that sir will be taking. And Banerjee, I'm sorry I could not get time last week, and I could not derive that expression for that delta V naught in the adaptive on time. So maybe you can ask sir in the tomorrow session. So he will be clarifying your query. And also you have asked me another question today, which I have told you to ask sir. I have forgotten which question you have asked me. Do you recollect which question you have asked me today? Which I
Yes, sir. It is like assignment 10, 6
Yes,
question.
yes. Assignment 10 question. So you just update in the docs. I will talk to the TS so we can update in the doc file which sir will be using to clarify the doubts. So these two questions you either ask in the forum by today, or you update in the Google Forms that has been shared by the NPTEL, and we'll forward it to sir, and sir will discuss tomorrow. And this is point number one. So tomorrow is the final session that sir will be taking in this course. So if you have any questions from week 1 to week 12 regarding any concept, any simulation, hardware, any derivation, anything, you please ask sir. Sir will be clarifying these doubts, and after this there will not be any interaction between you and sir. So take this very seriously and ask as many questions as possible that you have, and this will be the last interaction with sir before your the final exam as well. So keeping that in mind, you can also ask him, like, if you have any questions regarding, say, what type of questions you can expect, any questions you can ask sir. So sir will be able to help you. And this is all about tomorrow's session. Yeah.
Sir, one more thing is, like, in the case of controller design, we have to remember few of the equations, right?
Yes. Some basic aspects. One thing is,
it seems difficult.
Say PID controller, you either can remember PID or you can remember the GVD of S transfer function, and then you can perform the small signal pole zero cancellation, and then you can get. But again, it depends. Like some bare minimum should be remembered, like KPK, KD. Usually we will not ask KPK, KD. So we will first ask you to derive that transfer function, and from there we'll ask you to perform pole zero cancellation. So it will be like a comprehensive question. So it is not just we'll give entire thing and ask KP. In my problems, I have asked in such a way because to completely explain and see how we'll get KP. But in the case of exam, I think it will be some comprehensive questions. So they will ask you first to derive GVD of S. What is Q? What is omega naught? What is the numerator? What is denominator? Now, if I cancel it with the PID controller, what is KP, or what is K1, what is K2, and now what is KP, what is KD, and now what is KPD, what is KD, what is KDD. So in such scenario, you only have to remember GVD of S, and remembering that, you have to know how we are getting PID controllers using which you can get PID and then digital PID, KPD, KDD. But yeah, some aspect of the things you remember, and this is like eternal in every course. It is not that everything we can derive from scratch. So in any course, there are some standard results which we have to memorize, and yeah, that is there in every course. So in this course also, there are some final results that you have to remember, because GVD of S you cannot derive in the exam. That is not a good idea. PID you can derive in the exam, but you should also balance between your time as well as how much you are planning to derive in the exam. Not every question will be formula based. Some questions will be formula based, and there you need to spend some time. Calculations will be there, but other questions will be somewhat straightforward. Few questions will be very easy. Few questions will be theoretical, where you just have to know the theory, just have to remember the concept, and you can answer it in few 30 seconds, few tens of seconds. And some questions like very long, you just have to go through line by line code, and they might ask which gate does this code represent, which will also take few minutes. And if you consider PID, it will take some extra time, 5 to 10 minutes, where you have to do all the step-by-step calculation, but not all questions will be like that. Whatever problems that we have solved, whatever questions that have been asked in assignment, similar type of questions you can expect in the exam. So what all results that are needed to solve the assignments, same results you will be using in the exam also. So that is, yeah, that is there. Okay. So the announcement one is we'll be having a live session with sir tomorrow. And the second announcement is, as you know, next week is the last week, week 12. Next Monday, I think it is 9 plus 7, 16th October, 6 p.m. to 8 p.m. our final 12th week session between you and me. And after that, I'll be taking additional 1 hour session where I will be summarizing everything that we had discussed, or we can solve few problems. So it is again up to you. The official announcement will be given to you. So I have discussed with the NPTEL team and I have given the slot. It will be next Wednesday, which is 18th October, 6 p.m. to 7 p.m. I'll be taking 1 hour session. So if you want me to summarize what we have discussed in the 12 weeks, I can do that. If you want me to only solve problems, 5 to 6 problems, I can also do that. So maybe you can let me know your thoughts accordingly. I can prepare the slides. So there will
Summary,
be
sir.
summary. Okay, okay then.
The problems can be shared through slides as well.
Okay, okay, yeah, that is a good idea. So I'll prepare a half an hour summary and half an hour problem. So maybe 2 to 3 problems. And if you want, I can give some additional problems for you to solve depending upon my availability. Everything we'll see, and convenience also. So yeah, that is it. Tomorrow we have live session 5 to 6. You ask doubts, you submit the doubts through forms, and sir will be discussing. And next week we have week 12, 6 to 8 p.m. which will be next Monday. And after that, Wednesday, 6 p.m. to 7 p.m. I'll take one final session before your final exam, where we can have some doubt clearing session. First, I'll try to summarize what we have discussed from week 1 to week 12, where from which topic you can expect questions. I can maybe let you help with that, and if time permits, we can solve few problems. Yeah. If you have no more queries, we can end this session.
Good night, sir. Thank you.
Okay. Yeah. Thank you. Then good night. See you in the next week.
Thank you, sir.
Yeah. Good night.